Oh joy, another snow day. We're going to take you back 2 days of limits today. So quick refresher, if you're doing the limit as your x value approaches infinity, you can multiply the numerator and denominator by 1 over your highest degree term, and then it makes it easier to see what terms are going to go to 0. So if we multiply this one by 1 over x cubed over 1 over x cubed, you'll end up with 1 over just 3 plus 1 over x to the third, which the limit of that term will go to 0 as we approach infinity, and we'll just get 1/3. So we're talking about limits that can't be done so easily today. They're going to be limits of what's called an indeterminate form, which means you can't determine its limit directly. The two types that we're going to use this special thing called L'Hopital's rule on are the type where you get 0 over 0 when you try to do your limit, or infinity over infinity. There's lots of indeterminate forms, but those are the two you can use L'Hopital's rule on. So first off, deciding if you have one of the two indeterminate forms, if you take your limit as x approaches 0 of sine x over x, plug in 0 to the top, 0 to the bottom, guess what? You get 0 over 0. So that's an indeterminate form, and it's one of the ones we can do with L'Hopital's rule. For this one, if you try to evaluate your limit at 0, you just get 0 over 1. Which means the value of this limit is just equal to 0. You don't need anything fancy. It's not an indeterminate form. If you try C, as your x values approach infinity, you're going to have e to some really big value, so 2 to some really big number. You're going to end up with infinity over infinity, essentially. Really big number divided by another. So yeah, indeterminate form. To use L'Hopital's rule to evaluate some limits, first check that it is one of those two indeterminate forms. Then you actually take the derivative of your numerator and denominator separately. If you find the value of that result, that limit is actually equal to the value of your original function's limit. So first thing to do is check to see if you have an indeterminate form of the type 0 over 0 or infinity over infinity. We do. If we plug in 1, we get 0 over 0. So I'm going to use L'Hopital's rule to take the derivative of the top and then the derivative of the bottom, and then try plugging in my value for x again. So if I do that, I'm going to end up with negative 12 over 5, which is equal to the value of my original limit, actually. That's what L'Hopital's rule says. If you look at B, before you blindly use L'Hopital's rule, make sure you have one of your required forms. So if you plug in 0 for your x values here, you end up with 0 over 0, which is, again, one of our possibilities for using L'Hopital's. So take the derivative of your numerator and the derivative of your denominator separately, and the value of that limit should equal the value of our original. So if you take your derivative, we get 1 over 1 minus x times it over the inside. Derivative of e to the x minus 1 just is e to the x. We could do a little bit of rewriting, simplifying here a tiny bit. So if you plug in 0, you're just going to end up with negative 1. So that limit's equal to negative 1. It's possible you might have to use L'Hopital's rule more than once. So if you try checking this one, you're going to have infinity over infinity. If you take the derivative of the top and the bottom, you'll end up with e to the x over 4x to the third. Guess what? That's still an indeterminate form of the type infinity over infinity. So you do it again. Take the derivative of the top and bottom separately. Repeat, repeat, repeat until you get something that you can actually find the value of the limit for, or it's no longer one of our indeterminate forms. So if you keep going on this one, it's nice that the derivative of the top always stays e to the x. Eventually you get e to the x over 24 as x approaches infinity, which if you plug in that value, raising e to some really large power, that's an infinitely large number. So this limit actually doesn't even exist. It's going to approach positive infinity. All right, hope you're having fun because we have a few more to talk about. We're going to look at one more like this and then a couple more where they're not in the right indeterminate form. So If you look at this last one of the kind of easy ones, it is a form infinity over infinity. If you take its derivative, you'll have 1 plus 1 over x over natural log of x plus ends up being 1 because you have to use product rule in the denominator. And then thinking about as x approaches infinity, what's going to go to 0 there? What are you going to end up with? So you're going to have that term that's 1 over x. That's going to go to 0 as x approaches infinity. The denominator is just getting larger and larger and larger. Natural log doesn't grow very fast, but it just keeps getting bigger and bigger and bigger. So you have 1 over some really big value. It just keeps getting bigger and bigger in the denominator. So the value of that limit is going to be equal to 0. If you actually made it that far in our lovely L'Hopital's video, awesome, fantastic. You're one of my favorite students. As bonus, if you write my lovely cat's name at the top of your paper, I'll give you a bonus point on your homework. Oh, kitty. This is Inya. She says hi. Okay, so if it's not of our two indeterminate forms, the special two indeterminate forms, we're going to have to rewrite it first before we can use L'Hopital's rule. So we're going to have to get a little tricky with rewriting things in indeterminate forms that we can use. This one's of indeterminate form 0 times negative infinity, which, yeah, we can't find the limit that way, and we can't do it with L'Hopital's either until we rewrite it. So, little trick. If you think of this as natural log divided by 1 over x, think multiplying by the reciprocal, that's the same thing. But now, if you let x approach in 0, you're going to have in negative infinity over infinity, which is one of the forms that'll work for L'Hopital's rule. So derivative, and then a little bit of simplifying, multiply by a reciprocal, x divides out, so you get the limit as x approaches 0 from the right of just negative x, which just ends up being 0. We're going to get fancy with some trig functions, which I know are your favorite. This is of form infinity minus infinity, which is a no-go for L'Hopital's. So you could rewrite cotangent as cosine over sine, and then see if you can go anywhere from there. Common denominator is probably a good idea. So multiply by x over x, multiply by sine over sine, rewrite that as a single fraction, and then hope for the best. So if you actually do it, and then plug in 0 for your x values, you do end up with 0 over 0, which is one of the indeterminate forms that we can use for L'Hopital's rule. Not so fun is the fact we need to take the derivative of the numerator and denominator to use L'Hopital's rule. So a little bit of product rule on top. You have cosine x times or plus the derivative of our second part, which would be x sine x, and then minus cosine x. Again, product rule on bottom. And then you're still not going to have some nice number. You're going to get 0 over 0. But that's okay. We can use L'Hopital's rule again. Take another derivative. Again, kind of messy with the trig functions, but derivative at the top, derivative at the bottom. And then once we do it this one more time here, if we plug in 0, we'll get an actual value. So thank goodness we're not going to have to do it a third time. Plug in 0, you just end up with 0 when it is all said and done. We're skipping part C because that one's super ugly, and yeah, I'm not going to put you through that without me. So very last one actually is of form infinity over infinity already, so we don't have to do any fancy rewriting. Just have to remember chain rules, so 1 over the inside times derivative of the inside, and then 1 over x. Divide out your 1 over x's is kind of key here. If you don't, you're going to end up going nowhere. But then that just leaves you with something that you can think about as x approaches infinity. Again, we talked about this earlier, but natural log x just gets bigger and bigger and bigger, so you end up with 0.